Yeah, I think so. I couldn't find the actual version too, and then last night I texted Elizabeth. Because I saw like the people who
the good thing is the one from last year was like a lot longer,
yeah.
right?
So I did some extra things, and then there's like one question that I didn't do. That was on this one.
The last question?
Yeah, so it wasn't a big deal, but I was like, oh, I feel stupid, because I was complaining for a long time about making this bag. I didn't have to do it.
I'm sure though you never just did things that like will happen.
Yeah.
Like it's definitely
It wasn't a big deal. I was just like, oh, Jack, that was dumb. I didn't know the syllabus was more than 30 pages long.
Okay. No, it's like, I feel like even the first assignment we did,
Yeah.
I think I did the version from last year.
I did too.
And then there were like, not major differences, but definitely some,
I didn't know.
some slight ones.
Differences.
I don't think they matter.
I don't think anyone said anything to me about my first assignment.
I got like a lot of other random stuff. Like dollar stores there are unbelievable. So, like I went to a 5-story dollar store, and there's like so much cool stuff in there. That's all just 100 yen. Your socks did not come from the dollar store, but like so many of the other souvenirs I got for myself did.
That's great for souvenir shopping.
Yeah.
I feel like a lot of times when you go to places to buy souvenirs, it's like expensive or cost or cheap.
So hopefully this will confuse her.
I think I saw her comment on some things that really stood out.
Hi, welcome back.
Thought about you all the time. Those are two very random things.
I don't care if they write them.
That is just some paper that I thought was great, and that is from this like 10-story paper store in Tokyo, and it just like looked really pretty, and I thought you would find some useful.
I feel like that looks like something that belongs in your apartment. I'm just kidding. Don't mind me.
I don't know like what
Yeah,
it says, what it says, but I'm just trying to
Big paper.
Yeah. So I have paper. This paper store is called Judy Atoya. It's in the Ginza in Tokyo, and like it is fantastic. We got some stationery.
I was like,
Tell me.
yeah. Sort of like a basic. It was like, they were like super shiny.
I haven't asked.
It was like a classic situation where my aunt.
I just thought that was fun.
I figure you probably would. It doesn't
You would find it used better than I.
This is like
And so I figured out, and I was like,
Yeah, you'll have to tell me all about it.
I would love to. And we are waiting for the QE today, right?
yeah, I mean, yeah, you're just like,
Okay.
it's just, you know, and what should I do with this information? I'm like, well, I'm more FYI.
Do we have,
They like obviously right up like that.
I think so.
On the right side, at least it's yours.
Let me double check my
I don't think that's it. I think that's, you know, really generous.
Oh my god, that's so
I think it's more just like, this is the way life is, and you're not conforming to it. And like,
how dare you?
yeah, it's that. It's that. It's like, never mind.
Oh no.
Yeah. Did you get anything this weekend?
I went to the beach.
Oh,
Okay, you were gonna come. Yeah.
I actually haven't been there. Is it?
It's fine. I'm not a beach person. I'd rather given the choice, I feel
Actually, I
relaxed.
don't know.
Yeah. And also, there's not like a town or like a central place where you can go. So that doesn't feel like a place.
Yeah.
It's just like
House is
always
always midnight.
Yeah, I just
Okay.
also happened that it was very similar.
like
I just want to go to the beach.
I've been
Fine.
really off
This
this
time
time
zone.
zone and
Every
like submitted it like
restaurant,
yesterday morning
every
and would just
Waves or kind of
like had a really light calendar yesterday. Or, you know, like a souvenir Saturday.
Yeah.
When
They
you're
have
meeting
that, and
today,
like,
and it's in
the
for meeting at like 3 a.m.
It
Tuesday
wasn't
morning. I was like, okay. I need to wait until my calendar like goes back to the correct time zone to figure out what my schedule is. Really sorry.
It's close to, it's like a man beach. Close to like this might be I like it's
Well, I suppose either the weather or the QE has kept people away, so we have a smaller.
There's like a central.
Oh, okay. Okay, makes sense. Alright, well, this will be recorded so they can always watch it later. Today we're going to talk a little bit more about functions because they're pretty important. And we're going to also go through a couple of other things that come up when you think about functions. So things like loops and conditional execution, which in SAS is the if statement. And then we're going to try and apply these things today with a guided tour that we do together to write some functions to do something for us. And that's going to be to write a really simple regression solver. We're not going to do a conditional regression solver because the equation is painful, but we're going to do a very simple linear regression solver. And you can, if you want to, in your free time, you can write it for logistic regression and say in your papers that you've written your own software to do the regression for you. It's very exciting. The activity will be probably for next time. You're gonna have an opportunity to work in groups to do some data management problems, and you're going to work on writing some functions to sort of encapsulate different data management tasks together. So functions really can fit in a lot of different types of applications, but it's really easy to write your own functions to do data management tasks in a way that makes sense to you. So to start with, I want to talk a little bit about loops, which are actually very similar to functions, which you'll see in a minute. But you know, it's very similar to the SAS loops that you're used to. And in essence, you're also familiar with loops because the data step itself in SAS is essentially a loop. It loops through each observation, and you kind of tell SAS what to do with each observation. Although you can also have a separate looping system too. And just a side note, it's important to talk about loops because you can always use them to solve a problem, but R has a lot better alternatives compared to loops, so you won't really use loops all that much, but it's good to have knowledge of how they work because, number one, you know, it's a good backup, and number two, it's really useful for simulations and custom distributions. If you want to solve a problem sort of empirically without actually computationally solving it, you can do it with loops pretty easily. And the way that we'll do this, which we'll see some next time, is there's a function called apply, which kind of it's a loop in a different way, and then you can do things with vectorized operations, which is kind of thinking about things using vector and matrix notation rather than individual observations, and you kind of write out the vector equation and it will solve it all for you at once. So a lot of this can be avoided, but it's still important to talk about. And you'll see this come up in examples too, so it's good to be able to recognize what it's doing. So you'll notice that the format is similar to a function body definition we saw before, in that it uses these curly braces. I call them curly brackets, but my father-in-law was a computer science major 40 years ago, and he insists that those are called braces. Much like the hashtag or the pound sign is actually an octothorpe. But anyways, you're going to have these braces enclosing the body of the loop, much like they enclose the body of the function. It's really similar to SAS in that, remember, SAS has for I in A to B type of format. So the idea is you're going through a sequence of numbers, and then you have an index that you refer to the current loop iteration with. It's just SAS. I mean, R has a much more flexible format. So the way it works is you still have to specify what the index or the loop number is. So that's the I here, the first thing. In is just I in, that's always the same. That's sort of separating the index from the actual thing you're stepping through. And then here I have an italics vector. That can be any kind of vector you want. So if you want to replicate the SAS behavior, where you write in from A to B by some step size, you can just plug in the sequence function into a vector. So I'll have some examples in a minute. But basically, you could say, for I in sequence from equals 1, 2 equals 10, by equals 1 would do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here's an example of a really simple loop. Can anybody figure out what this is going to do? With the hint that cat, if you haven't seen it, just print something out to the terminal. Any ideas? So we got for I in 1 to 10, cat, and then we've got some text here. Any ideas?
We'll just list iteration 1 of an iteration 2 of an iteration 3.
Yeah. So it just prints out basically for each iteration of the loop, when there's 10 of them, it's just going to print iteration 1, and then this is a new line character, so it starts a new line, and then it's going to iteration 2. So it'll just basically print iteration 1, iteration 2, iteration 3, iteration 4, iteration 5, and just substitutes in a value, each sequential value from the 1 to 10 into it. So the point of this example is I could put anything in that 1 to 10 space, and it would print out, instead of saying iteration 1, 2, 3, 4, 5, 6, 7, 10, it would fill in whatever was in the 1 to 10. So I could do 10 to 1, and this would print, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. I could put some custom sequence in here. Right, I can put an arbitrary phone number in this. Or I could use sequence to make some kind of other sort of custom sequence to iterate through. And you'll see here the way that I have the braces set up, you don't really have to do this. Like I could do this all in one line if I wanted to. But the way I like to do it is I like to have my brace lining up with basically where it starts from, so that I can easily check and see when it is supposed to end. And I've done the same thing with cat here. I don't really like having a bunch of functions all in one line because I lose track of where the parentheses go. But remember, R will not execute an incomplete statement until it gets to the end of a line and it's complete. So what you can do, and my preference is I like to break it up like this, where I kind of put an indent with each layer of complexity that I'm adding here. So I can see that cat wraps around this, and I can see the loop wraps around cat without getting confused. So here's my same example. You can put an arbitrary sequence here. And this is an example using something that's similar to what SAS does in the data step. So remember, in SAS, you can say something like x equals x plus 1 or something like that. And it'll add 1 to all of values of x. Well, you can replicate that in R using a loop, which is what SAS is really doing. So you can say for I in the length of x. So what that does is make sure that it basically goes through the whole length of the variable. Because length of x is going to return 7 here. So it's going to go 1, 2, 3, 4, 5, 6, 7. And then here I'm referencing the ith element of x on both sides of the equation. So it's going to pull out the same slot in x. So the first time this runs, I is going to be 1. Oh, sorry, this should be, it's not I in length x, it's 1 to length x. So, sorry about that. Because length x would just say, for I in, so length x evaluates to 7. Right, so this would say for I in 7. It would just plug in 7 and be done. So I have to actually make it into a vector. So if I put 1 colon length of x, it'll say, okay, well this is 1, 2, 7, so it'll go 1, 2, 3, 4, 5, 6, 7. Then it can step through that vector. But again, all this is really doing is it's saying, okay, for each thing I'm gonna take that element of x and add 1 to it and return it to itself. So it'll first do this for 8 and give you 9, then it'll go through 6 and change to 7, 7 changes to 8, and so on. And it modifies the x thing itself. So this is like a permanent change here. If I didn't want it permanent, I'd want to make another variable like that's a copy and edit that one. But here's a better way to do it in R. Remember I said you could vectorize stuff? So if I just wanted to add 1 to everything in x, I can just say x equals x plus 1. And R knows that since it's a vector and I'm adding 1, what I really want to do is add 1 to every element. So it can kind of interpret things and make it work. Now if x was just one value, you know, if x was 5 instead of being a vector like this, it would still work, right? It would just add 1. So this is a common, yeah?
So if you just print out x after this, it would just be 9, 7, 8, 6, 4, 1, 10.
Mm-hmm. Yeah. And then x itself would also be modified. But I often do that when I'm doing a loop like this, is I'll print something out to like debug it and make sure that's actually doing what I think it is. Yeah, but that's exactly right. So the theme here is that R will adapt. You can use the same code for multiple things, and depending on what data type you have in the objects that you specify, it'll do different stuff. So it's, you know, it saves you some thinking about, oh, what's the right function to use, or what's the right syntax. You know, there's a lot of things that have the same syntax. It's interpreted differently. There's 2 other types of loops you can use in R, at least 2. There may be more, but I really don't recommend using these. They have a little bit of application in generating distributions. And this is an example of that. So, so I'll just kind of walk you through what's happening here. So first we're starting x as 0, and then we're going to say while x is less than 5, take x and add a random number to x. So what this is going to do, remember this, what while does is it's going to basically continue the loop until the condition is met. So the first time it tries to run the loop, x is 0, right? 0 is less than 0.5, so it says, okay, I'm going to run the loop. So it does this, it applies this function. So our runIf is not a conditional run statement, it's just our uniform distribution. So runIf pulls a random number from the interval 0 to 1. So you can imagine the average is going to be 0.5. So basically half the time this loop runs, if the runIf 1 returns greater than 0.5, it's just going to stop after one iteration, right? So half of my answers when I run this is only going to generate one value, but I can do it multiple times. Half of my answers are going to be greater than, they're going to be in the interval 0.5 to 1, right? Because all of these kind of exit the loop. And then I'm going to get something confusing, because if it doesn't break 0.5, it's going to basically pick a value and then like redraw from the distribution, add it again until it exceeds the value. So let me just, let's run this and see what the distribution is, just to show you that this is, you can create basically anything you want, and this is a really oddball distribution here. Didn't mean to close R. So also feel free to try some other loop to make another distribution of your choice, but keep in mind that it's possible to write one that won't ever end. It's not a huge deal, just press the stop sign. There's like a stop sign that appears when you run code. You can also go to, if you go to session, you can terminate or interrupt R if R is like frozen. This is how you like escape. But just to show you, here's, so we're going to set x to 0, and then we're going to say while x is less than 0.5, open the function, and close it down here. I'm going to say take x and add a random number. So just let me show you what runIf does. Okay, so it just generates a random number from 0 to 1. Thank you. So now if I have this whole block here and run, this is going to give me, oh, let's look and see what x is. Okay, so now it's 1.33, and if I try running this again, I'll get 0.5, 0.5. So, you know, I have no idea what this looks like, but I can easily write this into a function with no arguments. So again, this function is just going to basically replicate what I just did. So here's what was on the slide. And all I'm doing is printing out the answer, and then I'm wrapping it up in this make function. So now whenever I run make, or let me call this draw, because that's kind of cooler. It's like a drawing from a distribution. So now whenever I run draw, it's gonna run that whole thing. So here I've combined I've got a loop within the function. So this is basically, I really only use loops within functions if I'm going to do something like this. But if I want to see the distribution of draw, I need to do it a bunch of times. So I can use, we'll cover this later, but you can use the replicate function to say I want to run this function a bunch of times. So I'm going to run this 1,000 times. What if I don't run here? I think I replicated 1,000 once by accident. So I need to say that the function, yeah, I did it backwards. So the function I'm replicating is draw that I wrote, and I've got 1,000 times. So if I error unused argument, oh, what do I need to say here?
Maybe take the parentheses.
Oh, you're right, yeah. So in this replicate function, I can specify the function by name. I don't need to. Maybe I need to actually also tell it that it's replicate. Oh, it's expression. I was looking at the wrong page. Okay, so now it's running. So draw without parentheses is the function definition. So now, okay. So basically, just try until it works, right? Just fiddle with it. A terrible lesson, but okay. So now I've generated a bunch of draws from its distribution, and if I plot it, I can try and see what it looks like. So I was trying to come up with something that would be simple and a cool distribution. I've not really accomplished either, but I'll show you what this produces. I thought it was kind of neat still, because it wasn't what I expected. And if you do this with more replications, what you get is basically this is what I knew about here, from 0.5 to 1. This is basically some part of that distribution, and then the rest of the distribution is stacked over here somehow. Again, I don't understand, but if you run this lots of times, this is the distribution you get, right? And the point is you can make any kind of weird thing using some combination of like looping and redrawing stuff. There's a lot. I've read a lot about this in the biostatistics literature because I had to do a similar thing where I had really arbitrary distributional shapes that I was trying to replicate. And you can build it all from uniform distributions. You can extrapolate to every type of distribution from uniform if you think about it correctly.
So what does that one again mean?
So one just means pull one value.
Oh, okay.
Oh, like this one you mean?
That one.
Yeah, yeah. It just means pull one. I think that's right. I think it just has an n equals argument.
And that uniform distribution is constant between 1, right?
Yeah.
Right. So why are you values above 1?
Oh, so it keeps adding until I exceed the threshold. So the while. So I always get a value from 0 to 1. Yeah.
Okay.
It's because of the while. So the while says keep trying until the whole thing's at least 0.5.
Got it. Okay.
But then if the base when so when you draw a number from that 0 to 1, that say if you draw 1 which is 0.9.
Yeah. Yeah, the 0.9. So hold on, let me draw out the whole thing of what I think I figured out. So this, I think what's happening is this is 0, this is 1, and I don't have the right scale on here. But basically, for some reason, this goes up to like 0.8. This is 0.8, and then I think this is 0.5. So I think what's happening is like all the things that got picked above 0.5 in the first draw all go in this area. So it's basically half of all the draws going here. Right? Then on the next draw, half of the ones get above 0.5 and half of them get drawn again. So basically this is now like this or something like that. So this is, trial number 2. And I don't know exactly how it works, but it's something like this or something. I don't know. But the idea is like over multiple iterations it keeps adding. So the height of this bar actually includes the ones that basically got over 0.5, and then the next draw they like only had a 0.6, and they kept going. So it's like a really complicated iterative thing, but it comes out with this nice like shape overall somehow. I'll try and make a graph that I'll post that basically has different colors based on how many draws, so you can like see where the stuff is coming from in the distribution. But this is just an example of like what you would usually use a loop inside of another function, so that you can control what you're getting out.
And another nice thing about loops is you can loop over anything. So in
Yeah.
the future, that means you can loop over all the files in a directory and then process them all at once. So
Like let's say you have a bunch of data sets. You can say, while, or for all these data sets, go through. Yeah, good point.
Yeah.
Or model objects, yeah.
Or you can also just like, you use the replicate function instead of using that. You can add another loop, say.
Oh, yeah, and just do this multiple times.
Yeah, so
Yeah.
you can show that you can have 2 different, what do you call that? It's looping, there are 2 loops.
Yeah, so you're saying I could do, I can now have my actual make function is going to be a function of something. And remember, I can put in something here. So like if I want to change 0.5, I could make this the threshold, and then make that sub in down there. Like let me put function of tr, x is less than tr. So now I've got, now I've got a draw that I can experiment with and see how does it matter if I 0.2. What I could replicate this, or I think what Shadron was saying is you can have another function called here it was make, which is a function of, and I can continue this threshold idea. Now I can have replicate in here. Is that what you're saying?
Or you can, I was thinking, you can actually nest a loop inside of another loop. Basically, you are drawing this 1,000 times,
so
right? Is that 1,000 times?
Oh, I see. So you say for I, yeah,
The original
I in 1 to n.
Yeah.
And I can say, okay, well, I'm going to specify the threshold and sample size.
Yeah.
And I can say for I 1 to n, and then I could do all these things.
Yeah.
And then, see if this does what I think. This is getting too complicated for me to be able to do without. But okay, for I in 1 to n. Oh, I need to like make a vector for the output. So we're gonna say repeat in a. So basically, we're gonna make an empty vector to store stuff in. Then we're gonna say for I from 1 to n, I think we say y I is x, right? Because that'll like save it. And then what else did you say was?
Yeah, you're missing one bracket.
Oh, okay. So there's another 4 bracket that I'm missing. Doesn't this one go with this guy, or is this not?
Directly after need a left bracket.
Directly after the 4i.
Oh, I see. Yes, this one's missing. Okay.
Yeah.
I like didn't have it intended enough. Okay, let's see if this monstrosity will compile. Okay, so something's happened. Let's see what happens if we draw. The threshold is going to be 0.5 again, and n is going to be 2,000. Oh wait, maybe we have to make it output something. Yeah. Okay, so we're going to have it report y at the very end. So I can post this code too because it's already gotten pretty complicated. But the idea is, let me rerun this. So now I'll run this to redefine the function, which is now a nested loop, and then here is my draw function, which does it. So now I can make a histogram, Oh wait, this is, but I want to do make hist. Oh no, that's right.
It's just y, right?
In equals. Wait, where was I even working on this?
Yeah, draw that part.
This part, okay. I want to make a histogram of this. Sorry, y'all. And then here's my histogram. Now, if I increase the draw size, I can really get the thing that I was talking about, which is, make this like 50,000, and pray that this finishes. Okay, so you can see here that it's getting a little bit better, and I need to make it. What do I want? How do I make this frequency? Maybe I can do. Let me look at his, because I want the y-axis to be like not a count, but the actual like proportion. So freak equals null. Let's see. Oh my.
Maybe we should not do.
Yeah, I think we've angered the gods here. Let's just try one more argument and see if there's more thunder.
Just stick with count.
Equals frequency equals false. Okay, I promise I'll stop after this. Okay, well, it's still not what I got when I was writing myself, but the idea is there's different distributions you can make, and you can combine stuff pretty freely.
But I got distracted by the thunder.
Oh,
What does
no
freak
problem.
do?
So freak equals false. So here it just changes what my y-axis is. So I've got density here. So if you multiply density by like the width, you're going to get units of like probability. So like even though this is above let me just draw what the distribution for a uniform. So like a uniform distribution has 0, 1, and then if this is density, this goes to 0, 1. So like this area adds up to 1. So I could have like this graph, or if it went to 1 to 2, if this is density again, 0, 1, and if this is 2, if I have like a uniform distribution like spread out, it's going to be density 0.5 all the way. So like the idea is the integral of density over the what do you call it?
Possible value.
Yeah, the possible values is going to add to 1. So that's basically saying, okay, well this is basically above a uniform. Like there's more of these than there would be in a uniform distribution, and then these have like lower. So before, if I take this out, you'll notice I have counts on the y-axis here. If it runs. Yeah, oh sorry, frequency. Yeah, so this is actually like the number of actual draws. So if I'm talking about the distribution in the abstract, I probably want density because, but it's frequency would be better for like most data analysis probably, because you want to know like how many people. Alright, so there's one more type of loop that I don't recommend, but important to see. This is the repeat loop. So this one repeats forever until you tell it to stop. And this segues into our next topic, which is if-then statements. So here, this is a similar distribution. This is a similar idea where I'm building a custom distribution. I'm saying, okay, R, do this forever. Draw from a normal distribution. So one draw, mean 0, standard deviation 1, standard normal. And then if x is greater than 2, break. And if R has gone through this whole thing and hasn't hit a break, it like starts over. So what this is going to do is it's going to keep trying draws until x is greater than 2. So you're going to get a truncated distribution. So if the standard normal looks like this, and like here's 2, this is going to be a distribution of this part. It's going to be this tail here, where the total area adds up to 1, right? So I guess it's both, it's like a truncated but also like a inflated distribution, because it's actually taller than this would be in the regular one, because all of this stuff is getting pushed over here, but it has the same shape. So, I'm not quite sure what this would be, but maybe if I was modeling the tail of a distribution and like people's responses or covariates, I could do that. I know there's some, that would be an example, maybe exclusion criteria. Like suppose I have people who have some some value, and I know that I only have people who are sick in the study, and I know that the threshold for sickness is like 2, then this would basically pull a distribution of potential values of whatever the criteria for making the diagnosis could be. So this is an example of how, this is a different way of thinking about it. This allows you to have multiple exit points. So the while loop only has one exit point here. It just tests what's in the top. But you can have a branching structure with the repeat loop where you basically have to meet certain conditions in different ways and you can get out of it. So you might also use this for like a user interface. If you want to make an interactive program, you would have it break when the person hits the X button to get out of your program. So this sort of segues into conditional execution. Again, it's very similar to SAS, but it's just the syntax is different. The way R handles it is as a function, as it tries to handle everything. So the if function, similar to again, it looks just like the way that the body of a loop or a function works when you're like defining your own. But here you say if, and then what goes inside the parentheses is the condition to test. And then the body of the if statement is like what you actually do. So here's an example of how I might use it with some other options. So let's say I'm writing a function to make some plots, and I'm going to allow the user to set an option in the function. And I want to have different ways to handle the plotting. So here maybe I've got 3 types of plots. And I say, okay, well option 1 makes me the first type of plot. Option 2 makes me the second type of plot. Option 3 makes me the third type of plot. I have like a catch-all case. So what I do here is I say if option equals 1, so it just tests the value of option. And if that's true, it does what's inside the body of the if statement. I can follow that with an else if statement, which says only run this if the preceding if wasn't true, and then test to see if this next condition is true. So this kind of tests things in order, and you can have as many else ifs as you want. So here it's saying, okay, well this only runs if the if was false, but if this is false and option is 2, then follow this path. And then the third option, this else, is what is always at the end, and that's like, okay, well what if I can't match anything at all? Then it executes the last option. So this is like making breakfast in my household, right? So we'll get a bunch of bagels in bulk, and so my partner will say if number of pumpernickel bagels is greater than 1, make me a pumpernickel bagel. Else if the next preference is sesame bagels, try that. And then if nothing else, except toast or something. So this is kind of the way you're thinking about it here, is like an order of preferences for the program. It's going to try and test them as it goes down and find the first thing that matches. So this is really useful for making functions yourself, but I don't really use this much outside of like defining functions, because you can avoid a lot of this if-then stuff using vectorization and apply. So here's a direct comparison of loops in SAS and R. So I was saying that SAS has an implicit loop in the data step, and you have these things like if-then statements within the data step, right? So like if age is greater than 100, do something. So here I'm making a variable called old, and I'm assigning it values based on the value of age. So apologies if this actually isn't SAS code, but this is as good as I could remember. But the idea is like in SAS you're using an if-then statement, but it's not really an if-then statement, right? I'm not actually branching my program. I'm using it to make a test. And making tests can be done in different ways. If I really want to replicate the SAS structure as close as I can, this is what it would be, right? And this is doing the exact same thing. So SAS implicitly loops through all of the observations of the data set. Here I can explicitly loop through all the observations of age by using a for I in 1 to the length of age. So this will produce the same type of thing that SAS does. Here I have to explicitly say that I want the ith element of age. SAS already does that implicitly with this if-then statements. And I have to do the same thing when I reference a value of old. And the else appears the same way. Oh no, yeah, here's the closing brace. And I have to again explicitly reference the ith position. So this is one of the benefits of SAS is for this specific type of doing the work, it sort of does stuff for you, right? Like you don't have to write out the index because the point of the data step is you're always going, observation by observation. The downside is this isn't the best way to do it, right? A slightly better way here would be to use what we learned about square brackets and say, okay, well, I'm going to make a new variable, step 1. Then I'm going to assign all values where it meets one condition to yes, and all values where it meets another condition to no. So this kind of does the same thing, but avoids using the if-then statement, right? So this here is analogous to the else, right? Because what I'm doing is I'm starting it all missing, and then I'm assigning values one by one. So here I assign yes. And then my last statement here is saying, okay, if there's anybody that's still missing, assign it to no. So you wouldn't always use this in practice because maybe you have missing values for other reasons, but the idea is this is how you would emulate the same catch-all behavior. Because this might catch the same missing problem and assign them all to no. But the way that I would do it, which is the best way, is to just do it in a single test because it's only a binary variable. So here I would just say old is x greater than 100. So if x is greater than 100, old will be true. If x is less than 100, it'll be false because the statement's false. And if it's missing, old will be missing because it can't do the test for that particular person. So this is just an example of how yeah, it's really the same as in SAS, but you don't want to go about it that way. You want to try and avoid it. Yeah.
For the last one, would old be 1 and 0, or actually true or false?
Old and 0, but you can just multiply. Open the window a little bit. You can just multiply a true value by 1. Oh, thank you. To get. So if I did 1, I'll write in Blackboard bold here. If I did 1 times true, that's going to give me 1. And 1 times false gives me 0. So if you ever want to go from a true-false variable to 1, 0, you just multiply it by 1, and it'll solve it for you.
And you can do things we covered this before, like sum all the trues and falses, and it casts it to 1s and 0s,
yeah,
and those to treat as an integer. So Booleans are pretty good because you get the benefits of knowing it's a logical thing, and you can treat it as an integer pretty much all the time.
Mm-hmm. So I think that's actually pretty much the end of what I had. The last thing that I was going to do as an activity is to talk about how you would write a solver for a linear regression, but that's going to be kind of difficult to do. So I might just send you some code later you can look at. I guess I can tell you a little bit about, I guess this board is actually a little bit lighter. It's right in the corner here, but the idea, which you'll be able to see in the code, but I can just talk about how it works, is basically when you're doing a regression, for most regressions you're doing in epidemiology, you're going to use something called maximum likelihood estimation. You may or may not have gotten to this point yet, but what MLE does is it says, okay, I've got my data, which I'm going to call X in the abstract. And then I'm going to make some equation about my data, about how I think the world works. And I'm going to have parameters in that equation denoted as beta. This is capital beta. But we're used to things like beta 0 is the intercept, beta 1 is this variable. But basically beta is just, this is all of the parameters together, right? So you can think about, you're trying to choose parameters that fit your data in the model. So the question is, how do you make a computer do this? Computers are stupid. The way that they do it is, okay, a computer is good at maximizing or minimizing things. It can try things and find the minimum. And you can write a function to do that yourself. So what they did was they invented something called the likelihood function with a curly L. So what L is basically, it's a function of the data and your parameters. So the idea is I'm going to take my actual data and I'm going to take a set of hypothetical parameters. You may have heard this called fixed as actual, I think, is common. I don't think it means exactly the same thing, but it's the same idea, is that this is your actual data, and then you're going to plug in your guess at what the parameters are, and then I'm going to get out a value that represents how likely this is in some sense. And so the way that it's done, just because it's simple, is we're gonna find the probability of each individual observation. So P obs I, right? And I'm gonna multiply them all together, right? So it's just flipping coins. This is the specific case for conditional logistic regression, right? So this is written much more complicated in your classes because it's like, oh, well, for people who don't have the outcome, there's one probability model. For people who do, there's another, and like based on your covariate. But all it's doing is you have some probability model, which is just the thing that you write out when you feed it into SAS or whatever. You know, you have the logit of P is equal to like beta 0 plus beta 1, x1 plus beta 2, x2. So the computer, for the most part, just ignores this, right? Just whatever. So we're just going to focus on this and do it on a linear scale. So, well, I mean, I guess it follows here, but you don't really have to think about it. So what it really does, it just multiplies together the probability of each person, like having the observation they did based on what we think about the model. So all the computer is doing when it solves maximum likelihood estimation is it just tries different values of B, which is your like guess at parameters, until this function is minimized. Sorry, maximized. So remember, this is the likelihood. What it's actually doing is minimizing the deviance. The deviance is, I don't remember the symbol for it, but it's -2 times the log of the likelihood. And I'll show you why this is just important to think about, like just to see what's going on. The example I was going to show you today is going to be a specific case of maximum likelihood estimation for a linear variable, which turns out to be ordinary least squares, right? It's actually the same, or the sum of squares. It's actually the same equation, and the way you can see that sort of intuitively is, so with least squares, you have like a line that you're trying to fit to a bunch of points, right? And you figure out what the best line is based on the sum of the square errors. So you find the difference between y and the predicted value. So here I'm representing those by these little shaded triangles. So if the points of the triangles are the actual points, the sum of the area you can think of as like this area kind of, because it's a square. So it's saying how far am I from the prediction. So I'm going to sum up all the prediction errors and try to minimize that, right? So I'm going to take the sum of y minus y hat, which is the predicted value of y, and square it. And the reason why we square it is because it makes them all positive, essentially, right? But the point of all of this is the 2 here is the same 2 that's in the deviance calculation. So when you're doing this maximum likelihood estimation, you're minimizing the deviance, and you're doing the same thing when you take a least squares thing. It's just you don't have to go through this rigmarole of making it into a linear thing. It's already linear, so you can just basically calculate this and solve it. So I'll post some code that shows you basically, it's really easy to do this. All you do is you have one function. So function 1 is like literally just an expression that is your equation, right? So you like type in your equation. So like, you know, y equals beta x. This is for a really simple case where there's no intercept or anything. So I just say y equals beta x, right? I got a really simple linear model where I just have this. So that's function 1. I can use function 1 to calculate the predicted value of every person, right? So what I do is I apply function 1 to my beta that I'm guessing, and I also plug in my data, and then I get out my y hats. So this is function 2. Sorry. Oh no, this is the same function. So so function 1 takes your guess and your data and produces the predicted values, which is easy. It just does this function. Function 2, oh yeah, there's only one function. You just basically plug in a bunch of values for this to do it manually. That's step 1. So if I plug in the true value, so like let's say the slope's actually 2. If I plug in the true value of function 1, I mean of beta, I might get a perfect sum of errors. Oh, yeah, sorry, this is confusing because I don't have anything to work with. I don't have my notes, but so function 1 is the actual model. Then you produce function 2, calculates the sum of the square errors. So this is also really straightforward because I already know what y hat is. Much like before, I was like nesting functions within each other. I can just nest the prediction function in my like bigger function. So then function 2 calculates the sum of the square errors, right? And then I can just find the minimum value by putting in different stuff. And there's different ways to do that automatically in R. One is, the one I want to show you was, basically, it's actually the same as with our, the other example I showed you, where you make a for loop, right? So you say for beta in, 1 to 1,000. So we're going to try all these values, right? And then in here, we're going to say, like, calculate the sum of errors, which is F2. And then I'm going to output it. And then I'll get a vector that basically I can plot the distribution of, much like I did with the other one, except it's going to be something like this, right? It's going to show me the x-axis is going to be the beta value, and the y-axis is going to be the errors. So what it'll do is I can look at graphically, okay, well this is the best beta value, right? Because it's the lowest sum of errors. With the maximum likelihood, it would be the lowest deviance. It's super confusing with that display, but hopefully you'll be able to see it in the code. And I'll put comments in there so you can see what's happening. But it's something to me that it's really not that complicated, but it's something that we like see is so central to our work. Like once I understood what it was doing, I was like, oh, this is like both kind of scary because it's so simple, and like, but it's also like there's so much room for improvement. But to me, it's kind of powerful to like be able to see how it is and do it manually. But you'll see that it's not. It's only a couple lines of code to do it yourself. So any general questions? I mean, I think this is kind of hard to do in the dark, but. Any questions about like loops or functions in general? Like any problems you've had with it so far? All right, we'll have some more time to practice next time with so much more concrete stuff. Did everybody okay with the homework so far? Is that due today or? Okay, so that's any last minute questions? Anybody stuck? Awesome. Yeah, no problem. Cool.
So we'll have more of it coming out probably today.
Yeah.
Next week.
So look forward to that.
Functions and loops.
Well, it's already a million degrees in here, so I won't keep any more. But feel free to ask me if you have questions, and I'll post a brief. I mean, this is all optional, but to me it's helpful. So I'll post a brief write up of this and stuff so you can try yourself if you're interested. But yeah, thanks for bearing with me. Wait, the hallway has lighting.
Yeah, let's put it there, emergency.
Oh, maybe so, because the classroom across the way doesn't have lighting.
Yeah.
Sounds crazy.
Interesting.
Somewhere has power that because the internet's still running, or the internet is.
Oh, that's weird. Yeah. Which presumably, I thought there was a router in here, or maybe that's on the. That must be the hallway tower. Yeah.
It's interesting that they may consider internet like emergency power.
Yeah. I mean, it should be communicating. Let's see if the phone works. Yeah, the phone's on.
Yeah.
Weird. Though this doesn't work. Interesting.
Yeah.